Welcome everybody. In this video we will be discussing about the first principles method from derivatives. The first principles method is the very fundamental definition of derivatives, and in this video with the help of this first principles method I will be deriving for you the standard results that you've been using from derivatives. There is a high possibility that these are results you might have simply memorized and you might be applying them in a very mechanical manner. So if that is the case, do stick with me up till the end of this video and I can assure you that you will precisely know how these results have come into the picture. Now, I am not telling you in any way that this video is going to be easy. I am only telling you that it is going to be a little more focused on detailed discussion and mainly, like I said, the derivation of the results in derivatives that you've been using. Okay. So let us begin with the definition of the first principles method. This is your x and this is your y axis, and say for example you are plotting the graph of some function which is given by y equal to f of x. Just for the sake of our reference, let us say we are standing at the point A, and at the point A you need to realize that there is some x coordinate of the point A and the point A has some y coordinate also. From point A, let us say that we are moving on the curve up to a point B. At the point B also we have some x coordinate and we have some y coordinate. Now when I talk about derivative, if f of x was the function, we define our derivative as f dash x. Okay, the derivative of f of x is defined as f dash x, and that f dash x, the definition for it goes like this. It is the change in the y coordinate with respect to the change in x coordinate. So you will say that the change in y coordinate, okay, let's call it delta y. With respect to means divided by, the change in x coordinate means delta x, and the derivative, I mean you can call it the derivative only when the change in x coordinate is very small. The change in x coordinate is very small. Change in x coordinate being very small does not mean that the change in y coordinate will also be small. The change in y coordinate may be or may not be small, but this will be called the derivative only when the change in x coordinate, that is delta x, will be very small. That is, limit of delta x should tend to 0. So when I say limit of delta x tends to 0, I am ensuring to see that the change in my x coordinate is small enough, and under those circumstances delta y upon delta x is what is the definition of derivative of a function. Okay, now we need to just rearrange those terms, or we need to write them in a different way so that we can write that formula, or we can write that result in the form of a formula that we can use to solve our sums. F dash x will be equal to limit of, let us say that at this point the x coordinate was x, and at this point the x coordinate is x plus h. It is very clear that this distance out here is equal to h. Okay, basically the x coordinate is changing by an amount which is equal to h, So initially you were at x, you change the x coordinate by an amount equal to h, and you are reaching the point x plus h. Okay, correspondingly the y coordinate here will be f of x, because the y coordinate was f of x. The x coordinate being x, the y coordinate here is f of x. Here the x coordinate is x plus h. So if I put that x plus h in place of x, I get the y coordinate as f of x plus h, and that is why at the point B, the y coordinate which we have is f of x plus h. Now you need to realize that this length, this is basically the change in y coordinate. That change in y coordinate, visually you can make out it is f of x plus h minus f of x. So the change in y coordinate, which was delta y, that change in y coordinate has been substituted as f of x plus h minus f of x, and the change in x coordinate, we just saw that it was equal to h. Okay, so let's write that change in x coordinate, that is delta x, as h in the denominator, and limit of that change in x coordinate means limit of h was tending to 0. Now this is the formula of first principles method that we will be using for solving the questions. This is precisely the definition of derivatives, that is, derivatives simply means the change in the dependent variable, that is y in this case, with respect to change in the independent variable, which is x in this case, given that the change in independent variable is very, very small. Okay, so with this definition, these are the sums that we will be solving in this video. These are all standard results that you have learned in derivatives. That is f of x equal to x power n. So the derivative would be n times x power n minus 1. You have learned all those results, right? So those are the results that I will be deriving in this video, and we will be deriving them with the help of the first principles method that we have just learned. Okay, so let's begin with the very first one. F of x is given as x power n. To find the derivative, we need to apply the first principles method, and in first principles method, we need the value of f of x plus h. If I replace x with x plus h on the left hand side, we will have to replace x with x plus h on the right hand side also. So f of x plus h would be x plus h the whole power n. Now f dash x, that is the derivative, is defined as limit of h tends to 0, f of x plus h minus f of x divided by h. F of x plus h in this case is x plus h the whole power n minus f of x. F of x was x power n. We can simplify this by expanding that x plus h the whole power n in the numerator by using the binomial theorem. If we do that, we have x power n plus n times x power n minus 1 into h power 1 plus n into n minus 1 upon 2 factorial into x power n minus 2 into h power 2, plus that keeps on continuing up till you reach h power n. Of course, I am assuming in this particular sum that n will be an integer, but the result that we are deriving is applicable even if n is not an integer. So, I mean, that happens because the logic that we are talking about. Okay, I'll talk about it at the end of this sum, but for now, I have expanded it by considering that n is an integer. So the last term would be x power n. Had n not been an integer, then I would have had infinite terms after this. But the point is, all those infinite terms will be having the h term along with it. The only term that does not have h along with it is x power n, which has been written at the very beginning. Now, this is only the expansion of the bracket, right? We are missing that last term in the end, which is minus x power n. Okay, so minus x power n is what I'm writing in the end, and the whole thing has to be divided with h. You can see it very clearly that x power n minus x power n gets cancelled, and now every term in the numerator is having at least one h along with it. So if you take out one h common from all the terms and cancel it with this h in the denominator, then what you will be left with is something like this. H gets cancelled here, h gets cancelled here, and this term does not have any h left over with it. You can cancel one h from this term. But when you do that, this term will have h. The next term was a term in h cube. If you cancel one h from that term, it will be becoming equal to h square. The next term was h power 4. After cancelling off an h, it will become h cube. In short, every term after this term, okay, after the term which you can see in the blue box here, every other term after this term is going to contain at least one h along with it. So because of that, when you substitute h equal to 0 in this entire leftover expression, you substitute it to evaluate the limit. So when you substitute h equal to 0, you are left with n into x power n minus 1. That is fine. But every other term after that blue box term, after this term, is going to become equal to 0 because they had an h along with it. So plus 0, no matter how many terms you write, all of them are going to be equal to 0 only. So ultimately f dash x, that is the derivative of the given function, is n into x power n minus 1. So if f of x is x power n, f dash x, that is the derivative, is n into x power n minus 1. In case if the sum does not write f of x equal to x power n and they write y equal to x power n, then a different way of writing derivative is d by dx. It's not like d and d get cancelled, okay? That d is not a variable like x, y or z. It is something like an operator. You just write d by dx completely, and that d by dx basically means you are performing this operation on the function. That is, you are performing the operation of limit h tending to 0 f dash x plus h minus f of x divided by h. So d by dx of y, that is the derivative of y, with respect to x is going to be d by dx of x power n, but d by dx of x power n is equal to n into x power n minus 1. d by dx of y is popularly written as dy by dx. So let's write it in just one straight line. So dy by dx would be d by dx of x power n, and d by dx of x power n is n into x power n minus 1. That's precisely where I am completing that first derivation. So this is where we are done up till now. Let's go ahead with the second one, that is f of x equal to sin x. Okay, before we go ahead with that, let's discuss a few variations of this very result. If d by dx of x power n is n into x power n minus 1, then what would be the derivative of x? You will think that x is like x power 1, right? X, if it is like x power 1, then I can put n equal to 1 in this very result. By putting n equal to 1, I have 1 into x power 1 minus 1, but 1 minus 1 will be 0, and anything power 0 will be 1. So I have the derivative of x as 1 into 1, which is equal to 1. That is one of the results you can see from here. What about derivative of a constant? Any constant, any number which you have, that number can be taken out of the derivative, and you can write this as k into d by dx of 1. K is like k into 1, right? So whenever you have a constant into anything, take that constant outside the derivative, and you can say k into the derivative of 1. Now, if I want a 1 here, can I think of that 1 as x power 0? Obviously I can. So d by dx of x power 0, in place of n, I have a 0. So if I put n equal to 0, I have the derivative of x power 0 as 0 into something something, and that would be equal to 0 only. So derivative of a constant will be equal to 0. Third, what about derivative of something like x cube? X cube, right? So n in this case will be equal to 3. So the derivative is n, that is 3, into x power n minus 1, that is 3 minus 1, which will be equal to 2. In a similar way, what if we go for derivative of root x? Now this is one of the results you are expected to remember. Root x would mean x power half. Derivative of x power half, keep in mind n, the value of n currently is equal to half. So the derivative is n, that is half. X power n minus 1, that is half minus 1, which will be equal to minus half. And x power minus half means x power half in the denominator. So that will be 1 upon 2 root x. Okay. Then derivative of 1 upon x. When I say 1 upon x, it basically means x power minus 1. And n in this case is equal to minus 1. So the derivative would be minus 1 into x power minus 1 minus 1, that is x power minus 2, and x power minus 2 is basically x square in the denominator. So this becomes minus 1 upon x square. So these are two important derivations or inferences of this very result, and these two inferences are the ones that you need to keep in mind. Even the others are important, but specifically these two are going to be very frequently used, and every time you cannot waste time in deriving these expressions when a question comes in front of you. So the derivative of root x will be 1 upon 2 root x, and the derivative of 1 upon x will be minus 1 upon x square. Also derivative of x will be 1, and derivative of a constant will be equal to 0, and derivative of in general any power of x. To evaluate that, you can use this very formula, that is derivative of x power n will be n times x power n minus 1. Okay, with that we go ahead with our second result, that is f of x is equals to sin x. Like we have been calculating so far, f of x plus h is what we will find in our second step. If I replace x with x plus h on the left, I will replace x with x plus h on the right also. So if f of x was sin x, f of x plus h will be sin of x plus h. And by the first principles method, f dash x will be limit of h tends to 0. f of x plus h, which is sine of x plus h, minus f of x, which is sine x, the whole divided by h. Sine c minus sine d, sine c minus sine d, that can be written as 2 times cos of c plus d divided by 2, that is x plus h plus x, that is 2x plus h divided by 2, into sine of x plus h minus x, that is simply h, divided by 2, the whole upon h. Okay, now let's just split the limit. So you can think of this being one term and sine h by 2 upon h being the other term. We can also take this 2 in the denominator right here. So now the second bracket is very much in the form of a standard result that we have learnt in limits. Limit of theta tending to 0 sine theta by theta is equal to 1. So limit of h tending to 0 sine h by 2 upon h by 2 will also be equal to 1. So this bracket, let's just continue it here, f dash x will be equal to, this bracket will be equal to 1. And when we put h equal to 0 in this bracket, we have cos of 2x plus 0 divided by 2, which is equal to simply 2x by 2, which is equal to cos x. So we have f dash x equal to cos x into 1, which is simply equal to cos x. Okay, so if f of x will be sin x, f dash x will be equal to cos x. And if you want to write it in a different way, you can say that if y will be equal to sin x, then dy by dx, that is derivative of y with respect to x, that will be equal to cos x. If y equal to sin x, then dy by dx, that is f dash x, that is derivative of y with respect to x, will be equal to cos x. So that's how we have solved our second question. We go ahead with the third one, which is very much similar to the one that we have just done. F of x, if I take it as cos x, f of x plus h. Like we have been doing in the previous cases, if you replace x with something on the left, replace x with the same thing on the right. So f of x plus h will be cos of x plus h. And now comes f dash x. That will be limit of h tends to 0. F of x plus h, which is cos of x plus h, minus f of x, that is cos x, the whole divided by h. This will be equal to limit of h tends to 0. Cos c minus cos d is minus 2 sine c plus d divided by 2. That would be 2x plus h divided by 2 into sine of c minus d, that is x plus h minus x, which is equal to h divided by 2. And just like, upon h is also what is right there. And we will keep that h in the denominator of sine h by 2. And like we had done in the previous sum, we will take this 2 in the denominator right here. Okay, so limit of h tending to 0, sine h by 2 upon h by 2 will be equal to 1. So we have the last term as 1. And then we are left with a negative sign here. So minus sine of, put h equal to 0 here. So you have 2x plus 0 divided by 2, that is 2x upon 2, which is simply equal to x. So we have minus sine x into 1, and that will be the derivative of cos x. So the value of f dash x we just got, this was finally equal to f dash x. F dash x is what we are getting as minus sine x. Okay, so if f of x was equal to cos x, f dash x, that is the derivative of y with respect to x, which is dy by dx, is equal to minus sine x. Okay, so that's how we are solving our third question. And with that we go ahead with our fourth question, the derivation for tan x. Okay, so we begin with the fourth one, where f of x is equal to tan x. In that case, f of x plus h will be equal to tan of x plus h. And the derivative, that is f dash x, that would be limit of h tends to 0, f of x plus h, that is tan of x plus h, minus f of x, which is equal to tan x divided by h. Now here there are several ways of solving this question. I will go ahead with the way I feel is more comfortable. So we can write tan of x plus h as tan x plus tan h divided by 1 minus tan x into tan h. Apologies for those short forms which I am using, but it is going to help us save a lot of time. And just because it is simply a video, we have the liberty to use these short forms. I hope you do understand that if you're writing any exams, don't go for writing these short forms, because it's not allowed if you're writing any kind of official college examinations or even the board examinations. Just for the sake of understanding, in this video I am taking these shortcuts, and I do assume that yes, you do understand what I'm trying to convey by these terms. So just to save time, we are going ahead with these shortcuts, and don't repeat them in your exams. Okay, so if we combine the terms in the numerator, we have tan x plus tan h minus tan x and minus of minus, so that makes it plus tan square x into tan h, the whole divided by h. Now tan x minus tan x will be equal to 0. And from the leftover two terms, that is tan h and tan square x into tan h, we can pull out a tan h common. So that would leave us with tan h into 1 plus tan square x, but 1 plus tan square x is equal to sec square h, sec square x. And we finally have tan h upon h. So we will prefer to keep that tan h upon h separate from sec square x. And we know that limit of h tending to 0, tan h upon h is equal to 1. So this term can be substituted as 1, and into we are left with sec square x, so that is f dash x. So if f of x will be tan x, f dash x, which is basically dy by dx, is equal to sec square x. For all those who are wondering what is y, we always take f of x as y only. So tan x was itself equal to y. So f of x, which is equal to y, which is equal to tan x. If that's the case, then f dash x, or the derivative of y with respect to x, that is dy by dx, will be equal to sec square x. And that is how we are proving our fourth result. Okay, so that's how we have done this fourth question. In a similar way, we can derive the expression for cot x also. Okay, so f of x will be equal to cot x. In that case, f of x plus h will be equal to cot of x plus h. Let's go a little fast because the derivation is very much similar to the previous one. F dash x will be limit of h tends to 0. F of x plus h, which is cot of x plus h, minus f of x, which is cot x, the whole divided by h. Cot of x plus h is 1 upon tan of x plus h. Cot x is 1 upon tan x. And 1 upon tan of x plus h. Okay, that would be tan x plus tan h divided by 1 minus tan x into tan h. Okay, combine the two terms that you have in the numerator, and that should give you tan x minus tan square x into tan h minus tan x minus tan h, the whole divided by, we definitely have an h, but do not forget the denominators. So tan x plus tan h, we'll write that in one bracket, into tan x. Tan x minus tan x gets cancelled. In the numerator, you can pull out a minus tan h common. And we have tan square x plus 1, which is left over inside the bracket. Now tan square x plus 1 can be written as sec square x. And in the denominator, you have, we have tan x plus tan h into tan x. We will let it remain the way it is. Now, if you check, limit of h tends to 0, tan h upon h, that will be equal to 1. So the moment we write it as 1, we can simply substitute h equal to 0 and evaluate that final answer. So we have a minus sign with us, that is minus sec square x upon tan h was already equal to 1, so it's okay if we don't write it. In the denominator, it will be tan x into tan x. Okay, why tan x into tan x? It is tan h here. When we put h as 0, this will be tan 0, which is 0. So this will be tan x plus 0, which is tan x, into tan x, that is tan square x in the denominator. Okay, so that tan square x in the denominator, you can write it as cot square x in the numerator. But cot square x in the numerator is like sin square x upon, cos square x upon sin square x. Even sec square x is like 1 upon cos square x. So that cos square x in the numerator and denominator gets cancelled. and we are left with minus 1 upon sine square x. Okay, so that gives you minus cosec square x as the value for f dash x. And yeah, if f of x is cot x, then f dash x becomes equal to minus cosec square x, which you can also write as dy by dx. Okay, given that y will be equal to cot x, dy by dx will be equal to minus cosec square x. Okay, so that's how we have done the derivation for the fifth one also. And with that, we now go ahead with the sixth one, that is f of x equal to sec x. For sec x and cosec x, the derivation will be identical. So let's see if we can do them together. F of x will be equal to sec x, f of x plus h will be equal to sec of x plus h. F dash x is given by f of x plus h, which is sec of x plus h, minus f of x, which is sec x, the whole divided by h. Sec of x plus h is 1 upon cos of x plus h. Sec x is 1 upon cos x. Combine the terms in the numerator and that should give you limit of h tends to 0. Cos x minus cos of x plus h, the whole divided by h, into cos of x plus h into cos x. Now in the numerator, cos c minus cos d, you can write it as 2 times sine of c plus d divided by 2. C plus d would be x plus x minus h, that is 2x minus h, the whole divided by 2, into sine of, because I am not writing the minus here, the second bracket should be d minus c. So that d minus c would become x minus h minus x, the whole divided by 2. I'm so sorry, x plus h minus x, the whole divided by 2, because the other term was x plus h. X plus h minus x, the whole divided by 2, that would simply be h by 2. Okay, so now what we can do is we can keep this h along with the sine h by 2 term, and even that too we can bring it right here. And now we can say that because the limit of h is tending to 0, sine h by 2 upon h by 2, the value for this will be equal to 1. And when we put that value as 1, we can finally evaluate our answer, that is f dash x will be equal to, put the value of h as 0 here, it will be sine 2x by 2, which is sine x, divided by cos x plus h, that would simply be cos x because we are putting h as 0. So cos x into cos x, that will be equal to cos square x. Okay, sin x upon cos square x, we can write it as sin x upon cos x into 1 upon cos x. Let me just write that properly over here. So we are getting f dash x as sin x upon cos square x, and I'm telling you to write cos square x as cos x into cos x. Sin x upon cos x will be equal to tan x, and this 1 upon cos x will be equal to sec x. Okay, so if f of x will be sec x, the derivative, that is f dash x, will be equal to tan x into sec x. And that's how we have proved our sixth question. The seventh one is similar to that, that is cosec x. So let's complete it along with this only. F of x plus h will be cosec x plus h. Let's go ahead with f dash x, which is limit of h tends to 0. F of x plus h, that is cosec x plus h, minus cosec x, the whole divided by h. And cosec x plus h is 1 upon sin x plus h, and cosec x is 1 upon sin x. So when you club the terms, it is limit of h tends to 0, sin x minus sin of x plus h, divided by h into sin of x plus h into sin x, and in the numerator sin c minus sin d, that is 2 cos c plus d upon 2, so that will be x plus h, the whole divided by 2, which would be 2x plus h, the whole divided by 2, into sin of c minus d divided by 2. C minus d in this case is going to be x minus of x plus h. So that will become x minus h divided by 2, and that should give you minus h upon 2. Okay, so we have sine of minus h upon 2, which we can write as minus of sine h by 2. Okay, it's sine of h by 2. Okay, and yeah, with that we can start rearranging our terms. This h, we will keep it below sine of h by 2. We can bring our 2 right here. And finally, when we put h as 0, we realize that sine h by 2 upon h by 2, the value for that will be equal to 1, but the minus sign will stay as we go for our further simplification. So finally, f dash x will be equal to the minus sign which stays. Put h equal to 0 and we have cos of 2x divided by 2, which is cos 2x. Cos 2x divided by 2, which is cos x. The whole divided by sin x plus h. When you put h as 0, it would be sin x into sin x, that is equal to sin square x. And sin square x can be written as sin x into sin x in the denominator. Cos x upon sin x will be written as cot x. So we have minus of cot x. And this was also 1 upon sin x, which we can write as cosec x. Yeah, so that's it. The derivative of cosec x, the value for f dash x will be minus cot x into cosec x. Okay, that's how you're solving the 7th question. And yeah, with that we go ahead with our next result. So we have solved the 6th one, the 7th one, and we move on with the 8th one, that is f of x equal to log x. So in the 8th one we can say that if f of x has been given to us as log x, f of x plus h, like the previous questions only, this would be log of x plus h. F dash x is limit of h tends to 0. F of x plus h, which is log of x plus h, minus log x, the whole divided by h. Log of x plus h minus log x, that would be log of x plus h, the whole upon h. You can split the two terms, upon x. It was minus log x, so the denominator will be x. Split them, this will be 1 plus h upon x. What we can do is we can divide we can bring 1x here and multiply it with another x here. In this limit, the variable is only and only the term in h. So if I am writing an x, that x can be taken out of the limit right away. So this x can be taken out of the limit and we can say 1 upon x into limit of h tends to 0. Log of 1 plus h upon x divided by h upon x. So limit of k tends to 0, log of 1 plus k the whole upon k, that entire expression was equal to 1. This is a result that we have learnt in limits. So if I substitute this entire term as 1, I get the derivative of log x as 1 upon x. So if f of x is log x, f dash x will be equal to 1 upon x. Okay, let's go ahead with the 9th one. So we have proved this, and the 9th one, the 9th is a power x, and we will derive the derivative for that as well. So if f of x is a power x, this is the 9th one, f dash x, f of x plus h will be equal to a power x plus h, and f dash x, this will be equal to limit of h tends to 0, f of x plus h, that is a power x plus h minus a power x, the whole divided by h. A power x plus h is like a power x into a power h. A power x can be taken common from the two terms. So when we do that, we have a power x into a power h minus 1, and we will keep that h along with the term here. Limit of h tends to 0, a power h minus 1 upon h, the value for it is equal to log a. A power x can come out of the limit, so you have a power x into that entire other limit which you had, the value for which was equal to log a. So f dash x becomes equal to a power x into log a. So if f of x will be equal to a power x, you can simply say that f dash x is going to be equal to a power x, or if you say that y will be equal to a power x, then dy by dx will be equal to a power x times log a. Here there is a result that you should be knowing, that if you have, instead of a power x, if I give you e power x, if I say y will be equal to e power x. Let me just write that with a different color so that there is no confusion about what is the question and what is the special case. So if I give you y as e power x, then dy by dx will be e power x into log of e. So log of e will be equal to 1. For all those who don't get it, I have left a link in the description box below for the video that I have made on logarithms. Do check that video if you don't know logarithms, and if you are check that video for getting thorough with logarithms. It's a video that has come out really very well. So e power x into log e will be 1, so dy by dx will simply be e power x. So if y will be e power x, the derivative will be e power x only, because the other term, which is the log e term, becomes equal to 1. You might be wondering at this point of time that, sir, a power x, can't we write the derivative as x into a power x minus 1? You can't. I'll tell you why. When you say x power n, this was an expression of the type variable power number. Number means a constant, okay? So this was an expression of the type variable power constant. And when I say a power x, this is like a number which is a constant power variable. Variable power constant and constant power variable are two different things. That is why for variable power constant, you have to use x power n formula. That is, the derivative will be n into x power n minus 1. And for constant power variable, you will use the formula a power x into log a. That is how simply you can learn the derivations of all these standard results. So this is where I am done with whatever content I wanted to cover in this video. We have derived the derivatives of all these standard functions that you see in front of you. And the derivation has been done by the first principles method. I will just make a final summary of all the results that we have learned, and with that I will end this video. Okay, so we saw that the derivative of x power n was n into x power n minus 1. The derivative of sin x was equal to cos x. The derivative of cos x was equal to minus sin x. The derivative of tan x was equal to sec square x. Derivative of cosec x was equal to minus of cosec square x. I'm so sorry. Derivative of cot x was minus cosec square x. Derivative of sec x was equal to sec x tan x. Derivative of cosec x was equal to minus of cosec x into cosec, minus of cosec x into cot x. Derivative of log x was equal to 1 upon x. Derivative of a power x was equal to a power x into log a. A small inference of this was derivative of e power x will be equal to e power x, and from the very first formula also we had made some inferences, that is, from derivative of x power n equal to n into x power n minus 1, there were a few inferences that you had to remember, that is d by dx of a constant will be 0. Second was d by dx of x will be equal to 1. D by dx of root x, that will be 1 upon 2 root x. And d by dx, the fourth one, d by dx of 1 upon x, that will be equal to minus 1 upon x square. Okay, so with that I am done with whatever I wanted to cover in this video. I hope that whatever I have discussed has been somewhere helpful to you in your preparations. Thank you for watching.